psychiatrist.
Yeah.
That's it. I'm done. Yeah, thanks, Will.
Okay. I'll just go?
Yeah.
Great. So today we're going to be asking a classic question in neuroscience, which is, what is a good representation of information? And this is a nice question to ask because there's a lot of data about it, because you can just stick an electrode in and correlate some neuron's activity with a variable in the world, and you've got some measure of the representation. And you can build these links between normative theories of what a good representation should look like and the experimental things that you measure, and go back and forth, make predictions about new things if your theory is good, and inform your theories on the basis of so I think it's a nice question to try and ask. And just to go through one of the a simple version of this story is you can imagine the representation of this set of data. So every point is an input, and we imagine there's two neurons, A and B, and their activity is given by the position of each point along those axes. And so it depends on what you want to do with this representation, but we might define good in this case to be, can you separate the orange points from the green points with a linear hyperplane? Okay, so like linear decoding of orange versus green. So in this case, this is a bad representation because there's no plane, I've checked, to separate orange from green. But if you add a third axis that doesn't add any more information, but just reconfigures the existing information, then you can, as you can see, slice it with a hyperplane and decode orange from green. So I guess the points to take from this are that depending on the decoding demands, in this case orange versus green, or our computational limitations, which are we have to decode things linearly, we end up deciding that the second representation is good and the first one is bad. But you can imagine how each of these things could change. For example, you might want to decode different patterns of orange versus green, and then neither of them would be good, and you have to come up with some other representation. Or you can imagine having more flexible classifiers, for example, not just hyperplanes, and then you'd again decide actually the first one was good enough because you would draw this circle that separates orange from green. So some trade-off between these computational limitations and the things you're going to ask the representation to do to find what good is. And exactly these two kinds of arguments can get you a long way. People argue about this kind of thing for mixed selectivity neurons in the frontal cortex, or high-dimensional coding in the cerebellum to allow maximum decoding and things like that. So that's a classic vein of work in systems neuroscience. But I guess the stride away from that we're taking here is that not all representations are just doing best decoding. There are a lot of other things going on in your brain, and somehow they must be represented. And so we should be seeing signatures of those other tasks that the brains are performing, and that should be reflected in the normative theories we build for representations. So the particular thing that we think your brain is doing a lot that we're going to try and formalize and study is the concept of internal models. And so just to give a quick example of what that might mean, here's me. I'm planning a train trip from London to Rome. And so that's a navigation task. I've got to work out on this high-level navigation thing, the series of train trips I have to take through major rail termini in order to get from one to the other. And also I have to do other navigation tasks to get from where I live to the train station. So those are both internal models I might have that allow me to predict the consequences of actions that I might not actually have ever taken or ever will take, but know their consequences in order to plan the route. But this idea of internal models applies more broadly to tasks. So you might know there's a task, you could conceptualize having a ticket on a train as a task. You know that if you don't have a ticket, you'll get fined, and tickets are often on your phone, so you need to charge your phone in order to make sure you have the ticket to present to people. So various hypotheticals you can play out in your head because you have a model of how this ticketing process works. Or even beyond that, you have the classic internal models are physical internal models. So you need to know how to stack items of luggage on top of you so that during the rickety train journey, they don't fall on top of you, right? So these are all internal models of how processes work. You must have somewhere in your brain so that you can predict the consequences of hypotheticals. So this is the idea. Beyond just some functional constraints and biological that we were talking about before, we're going to impose this third one, which is that the consequences of unseen actions can be tested internally in your representation. So this, I guess, is, you should feel motivated now that we're going to be trying to pursue a representation G of a variable X. So X is some variable we encode. G is a vector of neural firing rates encoding that variable. I'm going to ask three things for this representation. The first is that different inputs, different values of X are going to be encoded differently so that we know what value X has, so it's a proper representation. Second is some biological constraints, which for us will be positive and bounded firing rates. And then finally, this actionable concept, which is supposed to be you can act on the representation in a way that mirrors the world externally and do planning and things like that. So this talk is basically crystallizing those three and studying some of its consequences. Cool. And the particular one we're paying a lot of attention to is grid cells, because they're quite a strange representation of 2D space, one of those spaces in which you'd like to do this kind of internal modeling and planning. And just to run through some phenomenology that we're going to be returning to for people who might not have seen it. A grid cell is a neuron that has the following properties. As the rat runs around, in this case a square box, the lines it's running around are the gray traces. If you put a dot every time this particular neuron fires, it forms a pattern that looks like a hexagonal lattice. So that's a grid cell. And there are many neurons who have receptive fields, i.e. the pattern of places in which that neuron fires, which are translated versions of one another, translated but not rotated. And so this collection of neurons whose receptive fields are translated versions of one another is termed a module. And in the entorhinal cortex, where you find these neurons, there are many of these modules, which are sets of neurons with this lattice receptive field, but whose lattices are different. And they come in disjoint, so it's like there'll be one at big length scale, this module 1, and then one at smaller and smaller, but not in between. So these sets of neurons that share the same translated basic pattern. And to quickly run through, there's been a lot of previous work trying to understand why this strange representation of space exists. So normative reasons for it that is kind of similar to our work. So for example, there's efficient coding arguments that are similar to our idea that you should be functionally encoding many different points. And I guess we're trying to add to that, why be gritty in the first place, or why align things so that you can't answer from a pure decoding point of view. Positivity has popped up in a lot of these theories of grid cells and will play a similarly important role for us. And then actionability kind of be related in a not so obvious as yet way to the mechanistic underpinnings that people have found, which are continuous attraction networks. So that's you can see these two as one's the mechanism, and hopefully ours is more normative, but hopefully they're linked some way. People have also done a lot of theories of things like ours. So you can imagine if you're doing path integration, that's very similar to being actionable and encoding all the positions. And people have claimed that training RNNs to do path integration leads to grid cells. And so again, it's similar to ours. There's been some recent debate. So for example, there's a Sorcha paper that came out in 2019. There's a recent version of it that claimed that you train a path integrating RNN, you get grid cells. And then someone came out and said, oh, maybe that's not true. And another paper came out and said, oh, no, wait, it is true. And then there's this tweet from the first author of the previous thing saying, oh, maybe it's in fact not true. So it's all got a bit confusing. I'm not really sure what the state of play is. But at least what we'll be doing maybe is providing a clear version that's not an RNN, in which you do definitely get grid cells, and explaining why. And it's most related to this sort of Tom and Eichenbaum machine or other ones by this group at UCL. So you can think of it as extracting from these kinds of models, specifically the Tom and Eichenbaum machine, the parts of it that lead the entorhinal module to produce grid cells, and explaining why it does that. So that's how we fit into the previous literature. And so I'm going to get rolling on our stuff now. I will set up the problem, which is the objective, the 3 parts of the objective I defined before. We'll then talk about how this relatively new constraint, actionability, leads to a very precise constraint on the neural code. And I'll try and talk through how that happens. And then we'll show that if you just numerically optimize, you get multiple modules of grids. We'll try and understand that in the second section and then make some predictions. That's the plan. So we're talking about this G of X. X is the position often on a torus. Everything's easier on periodic space, but we just approximate any flat 2D space by making our torus really, really big and approximating a finite section of 2D space with this large region of a torus that's basically flat. And sometimes I'll be talking about an angle theta. So if you see theta, it's just an angle on a ring. Sometimes it's easier to talk about 1D arguments as far as stuff. So the first of our constraints or goals was that we wanted different inputs to be encoded differently. And we'll do this with the following loss that we're going to try and minimize. So in the first term, it's got this measure of representational similarity. So this is small if the representation of 2 points, x and x tilde, are further apart than sigma. And it's large if they're closer than sigma. And so in trying to minimize this loss, you try and push all the points further than some neural length scale sigma away from each other. Then there's a couple of bits that weight this sum over all pairs of points x and x tilde. First of these is chi, and this says that points that are further away from one another are more important to separate than points that are very close to one another. And the way they're thinking of that is it's like a resolution on the so it's a resolution on the amount you want to encode space. You don't want to encode points that 1 micron apart very differently. You don't care about 1 micron differences. You care about kilometer differences. So those are the important ones to encode differently.
that in the neural space or in the kind of like manifolds?
This is the input space, the X space. So we've got a length scale in neural space sigma, and there'll be a length scale in chi as well, which is the length scale in the input space. And then finally, P will be something like the occupancy distribution of the animal. So in an infinite 2D world, there's far too many points to encode well, so you focus on the ones you'll actually visit, and that's the occupancy distribution P.
Are you going to tell us how whether point 2 is going to cause you grief in more actually circular?
In the actually circular world.
So, sorry, I forgot how to speak it.
Yeah.
So, we're treating the torus at the moment as flat plane, so everything's good, but it's not, right? Like in the extreme, like you wrap back round. So now you've got points that can look quite similar, but be quite far apart.
Yeah, so when we're doing things on circular spaces, we change our measure of distance to be like circular distance. So yeah, to get around exactly that problem. Yeah. Okay, so that's hopefully you'll agree that's some mathematical like codification of the ideas I was talking about before, being fast useful in this case. We also want to be biologically plausible, so for us that will mean positive firing rates and bounded firing rates. So you can separate pairs of points very well by just pushing all the firing rates to infinity. That's not plausible, so we're just going to give each neuron a certain amount of firing that it can distribute over the set of visited points how it wants. And then finally, this actionability one. So I'm going to go a bit more into that now. So this was the build on the idea that the world has like predictabilities, and you should build those into your representation. And since we're talking about 2D space, the predictabilities take this shape. If you start at the beginning of the red arrow and take the sequence of steps north and east and south, even if you've never been to this world before, you can know that taking one step west will get you back home. And you don't have, that's like a zero-shot inference about shortcuts, because there are rules in this world that north plus east plus south plus west is not moving. And these rules are consistent across all of space. And so what we're going to do is ask our representation to have these rules embedded in it, by which we mean every action, every translation in space, every step in space has a matrix that updates the representation in just the way it should. So W is the matrix that updates the representation W delta X according to the step delta X. Okay? So hopefully you're convinced that if you have this, you can do things like the zero-shot inference that I just mentioned. If you're at the end of the green arrow and you apply the matrix step west, your representation will update to its value one step west. And if you tied a memory to that location, like this is home, then you'll know that taking one step west will get you home. Okay, so hopefully you'll agree that if this way matrix existed, it would be as if you had an internal model in which you could do planning and do hypotheticals, things like that. Right. So it turns out that this places these W matrices are under a lot of constraints. And there's an area of maths called representation theory, which allows you to elucidate what those constraints are for the different structures of the variable you're considering. So here we're in 2D space. So the kinds of constraints we're talking about is that there's an step east matrix and a step north matrix and a step northeast matrix. And stepping first north, then east has to be the same as doing northeast. Things like that. Has to obey that vector addition. Also, east and west are opposites to one another. You do one after the other and you don't move. So the east matrix has to be the inverse of the west matrix. And a final example, these are just like examples to get you like see that there's a lot of constraints on these things, is if you do the loop, as I've been talking about, in this case in the other way around, so you get west and south and east and north, you get back to where you started. So the product of all of those has to be the identity matrix. So you get various constraints on what these matrices look like, and you can translate those constraints on the matrices into constraints on the neural code. Okay. It turns out that actionability, having these matrices, implies sparsity in Fourier space. So if we just go to the 1D example again and consider representing an angle theta, then sparsity in Fourier space looks like this. We'll give some intuition in a moment. But what this is saying is that your neural code is made up of some vectors, A0, AD, and BD, multiplied by sines and cosines. So you have this looks just like a Fourier decomposition of the function, but there's only a very limited number of frequencies in there. Capital D is smaller than half the number of neurons. So every neuron you add only gets you an extra half a frequency, whereas normally your Fourier decomposition has like infinitely many terms. So it's actually a very constrained formulation of it. So first, that will be very useful later on, but first I'm trying to give some intuition of where this formula comes from. So to do that, we're going to consider representing an angle with just two neurons. Then the equivalent equation, the structural equation that these matrices have to obey is that. there has to be some 2x2 matrix that updates your representation in just the right way to rotate it around. And I don't think it's too much of a stretch to imagine that this matrix is just a 2x2 rotation matrix. So your neural activity, as the angle swoops around 2 pi, your neural activity also swoops around 2 pi, and the matrix is the one that updates you appropriately to do the right rotation. There's an additional choice in here, in that all of the rules that I laid out in the slide before are satisfied for a matrix that rotates you around once, or one that rotates you around 3 times as the angle rotates once. So you've got a bit of a choice there. Yeah, so you can choose which one to do, and that's all in this, the equations will end up looking like this, a bit like this. Your neural activity traces out a circle, the rotation matrix rotates you around.
Or twice.
Or twice, or any integer number of times. I'm just going to conceptualize that as this neural activity doing this circle, and then the weight matrix W1 rotating you around it once. Okay. Now, the question is, if you had more than 2 neurons, what would the situation be? Well, turns out for 4 neurons, you just stack the 2x2 solutions. So in the 4D space, you've got one plane where your neural activity is doing 1 loop as the angle loops, and another plane where the neural activity is doing 3 loops as the angle loops. And these matrices obey the same rules composed together as the individual blocks do on their own. And now, maybe it's not too much of a jump to see how you get to the equation on the top of the board, which is for every 2 neurons you add, you get an extra frequency, an extra sine and a cosine. And the frequencies they're oscillating at is the omega d, these integers. And then all of these arguments only apply up to a linear transform. So you can think of these coefficient vectors as implementing some linear transform. So the circles don't have to be in their own planes. They can be like mixed together somehow, as long as they can be demixed in planes and then rotated. Okay, that's that equation. So here's a whole problem now. The step to 2D is also not too hard. So I've skipped that step, but basically you do the same thing, but on 2 circles at the same time. So here's our problem. We're going to try and minimize this loss function I talked to you about, subject to 3 constraints, 2 from biological plausibility, and 1 this actionable constraint. If the code has this form, you have the matrices that allow you to do consistent updates and do zero-shot inferences, things like that.
Sorry, just to come back to that thing that you just explained, I felt like I was following it until you were talking about 2 neurons, and oscillating between. Because I kind of felt like, okay, that makes more sense. Sorry, I wasn't getting the smooth circle in the G1, G2 bit. Okay.
Yeah.
But yeah, basically, I was following it until that point. But no,
the 4 neuron bit.
Yeah.
The 4 neuron bit, you just think of 2 neuron solutions stuck together in different dimensions.
Yeah. Cool. Thank you. But then you only ever considering it pairwise, like between. Do you know what I mean? So. Like, say you had another 2 neurons in that oscillation. That argument sounds to me like you're not then considering the pairs of neurons that could exist from the first pair and the second pair combined together.
Each pair you add, you fit another frequency in.
Okay.
And it does its own circle oscillating within them.
Okay.
Up to some linear rotation.
Okay.
Because so up to linear lengths, transform. So, yeah.
And why is 2 neurons not enough?
For what?
For this time, I mean, you can encode your angle with just the first 2, but you keep going and have D.
Yeah. Well, you could have only 1. And in the optimization, we don't force it to have non-zero coefficients. Okay. So it could definitely choose to only have 1 circle just going around.
You're just listing all the neural solutions that could
if you are actionable, you are this.
Yeah.
And then we'll later optimize over the choice of actionable codes to achieve our goal.
Optimize A, and B.
Exactly. Here's our game, here's our problem, and we're parameterized version of the code that is actionable, and we're going to optimize a set of parameters that define the code, these coefficient vectors A0, AD, and BD, and the frequencies KD, in order to achieve the other objectives. Because any code that has parameter like this is actionable. Good? Okay. If you do that for 2D space, you get this. So this is 64 neurons that you just optimize these set parameters. And see, you zoom in a little bit, it's self-organized into groups of neurons whose receptive fields are translated but not rotated versions of each other, i.e. modules. And some of them are definitely hexagonal, and some of them are less so. We think that's because we haven't done enough neurons yet. But
some of them it looks like the Fourier components, rather than being kind of like, it's like one has twice the frequency of the other. Like in that on the left, you have a solution along one axis, which is going kind of like twice the frequency as the solution that's going kind of like whatever the other diagonal. Does that make sense?
Yeah. Like the gap between rows is twice the size of the gap between elements of the row. Yeah. I'm not sure why it's chosen that. Okay. We'll get into it. The whole of the rest of the talk will be trying to understand why this is the solution. So,
and this larger module, they don't look like they're aligned, or am I just seeing that wrong?
Yeah, that one's worse at the alignment. Again, not sure.
You've got 3 different large modules. Right? You've got 2 pairs. You've got there's at least a set of pairs. Each one has a pair.
Yeah. See 2, and 3. Yeah.
Sorry, a line being like
same orientation.
But even those large ones have got a slightly weaker problem of what Will was saying. You know, where you get see how they appear to be slightly stretched in one dimension.
Yes.
Slight frequency difference.
Charlie, can I just also ask a question quickly?
Yeah.
So is this basically the asymptotic solution, or do you just stop the optimization when they look like this?
I just stopped the optimization once the loss appeared to stop decreasing. Who knows if it would have got better later on.
But could it also be get worse, even though it sort of satisfies the optimization?
Certainly, there are a lot of bad solutions that satisfy all the constraints, but are terrible codes. But hopefully, it's finding one because it's trying to minimize the loss. It's finding one that's probably quite good. Is the hope.
Do you know if, say, the thing that I was just talking about, where you have one frequency that's far up in one direction, do you know if the solutions that don't do that have a lower loss or a better optimization?
Yeah, I could set up 3 hexagonal modules, for example, and measure its loss and see if it's better than this thing. There's a lot of weirdnesses because you have to you can't just define the hexagons. You have to choose how they're aligned relative to each other and choose their lattice length scales. And so there's a lot of you're searching over quite a high dimensional space actually, even if you do that. And so you have to do you can't do a grid search even there because there's enough parameters to make it hard. So I haven't done that yet. Maybe that's the way I'll need to go. But my hope from some other simulations is that as I make it bigger, the kinds of questions you're asking will get answered. That has been true so far. So
presumably there's loads of interesting quirks here, because there's nothing where you set it up is of course in 3 modules. Right?
So
that must be
comes out
an interaction between the number of neurons and the size of the environment.
One of the parameters, sigma, the length scale in the neural space, actually gives you the number of modules, the ratio of that to the number of neurons. So that's part of the analytics that we do later on to try and understand why the solution gets you that. Kind of fun. You can change sigma and get different numbers of modules for the same population size.
Did you use Lagrangian optimization or just gradient based?
Gradient based.
But how do you enforce constraints?
You add a term to the loss that measures how much the constraint has been unsatisfied, and you penalize it for every not satisfaction. It's every time you get a negative firing rate, you add a big thing to the loss, and that's to minimize the loss.
There's been a good question in the chat from Harsha saying, besides the periodicity, is there some optimal distribution of orientations for a fixed frequency?
We will, I think, answer that if we don't ask again.
Cool.
Okay. So now we're going to try and understand why this is the solution to our problem, or at least why this is the thing that computer gets. So we'll do this in 3 steps. The force to be positive and the actionable will get us 1 module of grids as a good solution. We'll then see how separation encourages hexagons to form, and then we'll see how a fight between the separation and the previous modularizing thing leads to multiple modules. So we're considering this representation and has this constrained form. And so you can think of it as these orange circles in neural space, which are the cosine and sine looping around, and the green offset from the origin, which is the constant vector A0. Okay. So the bit that's really good at separating things is the orange circle, right? The constant vector doesn't separate points from each other. The orange circle separates points from each other. So just on the separation basis, you want to grow the size of that orange circle as big as possible. There's 2 reasons that's constrained, and there are other 2 constraints. First is you've only got a certain amount of firing that you can distribute over the position. And on this periodic space, so we're not yet in the flat 2D space, but just talking about the uniform distribution of occupancy over a torus, then you can do this integral. And this integral tells you that the amount of power, which is like the sum of the squared amplitudes in these circles, plus the constant vector, is a constant n, the number of neurons. So what that's telling you is the size of your circles, so the size of these AD and BD vectors, plus the size of the constant vector naught are a constant. So sum of the amplitude is a constant. That's what that constraint says. And so by the previous thing that says we want to separate points maximally, all this really tells you so far is that you should set the constant vector to 0, which makes a lot of sense, right? Because that doesn't separate any points. So yeah, that's maybe the first conclusion we're going to make. This is not the right conclusion though, because of we want it to be positive, okay? And some random sum of sines and cosines is not positive. You need to add a large offset in order to make it positive. So we're now playing a new game. The new game is the following. What is the smallest constant offset I can get away with while still making the code positive? Because that will have the best separation, because all the rest of the power will be in separating things from one another. So that's the game we're going to play now. Are we happy with that game? Good. Okay. So let's start. This is a sine. It's quite bad because you need to add a constant offset that's as large as the amplitude of the sine wave in order to make it positive. But this is made from only one frequency, and if we've got more neurons, we can use more frequencies. And so let's add a second frequency, and let's choose it to be the one at twice the base frequency, so that the minima are pushed up. Okay? Why do we choose that? Because then it makes this curve that's easier to positivize, because the minima are the bits that are constraining how easy it is to positivize. So if you add one up that pushes that level up, makes it easy to positivize. And you play this game again, and you're like, oh, how can I make the orange one more easy to positivize? Something that adds up all of the troughs, which is this 3 times the base frequency peak, making this red curve, which is again easier to positivize. Okay, and you keep repeating this argument, and you get something that looks a lot like a 1D grid cell, whose frequency spectra are some base frequency with the harmonics at decreasing amplitudes. Okay, so that was one neural response, but in order to produce that, we had to have many frequencies in our frequency spectra. But if you remember, each neuron only contributes like half an extra frequency to the population. So it's using much more than its fair share of frequencies to produce this good response. So the way that we resolve this is that across the population, sorry, this is a constraint. Each sine needs its cosine, and we have less than n over 2 frequencies in the total population. So the way that we resolve this is we build many neurons with the same set of frequencies. They pool their frequencies together, and all the neurons use the same set of frequencies, which means that the only tuning curves you can get are ones that use the same frequencies, but with different phases. And since like phases in Fourier space are like translations in real space, you just create a module of neurons whose tuning curves are translated versions of one another. Okay.
Is there any any evidence in the shape of grid cell firing pits that they look like this? I mean, everyone just treats them as a single line.
Yeah.
So, like, I'm just trying to think whether I think they are or not. I'm not sure.
I tried, but I think there's a lot of things that make just doing Fourier transforms on like spike, smooth firing rates very hard. Partly because you have to smooth them, right? Which like you're then convolving, which does a cutoff in Fourier space, so you're not going to see beyond some length scale anyway.
Yeah.
But I think I guess you can look at maybe if you look at like the ones on the front slide. I mean, maybe that's like just a sine and a cosine, added. That'd be my claim. Okay, let's go back to like
Sweeps and stuff, which could broaden them.
It's true. Yeah, it's true. I mean, it's hard to say the spatials of it, but definitely you look at like the dominant set of frequencies in the cortex, and they do have a lot of interesting harmonics. But then you have to believe there's some relationship between those and the shape of the sets, which not everyone does.
No comment.
This is a like direct prediction of your theory. It's like your grids are actually like really sharp if you have lots of neurons.
Yes. Okay. Yeah. So the extent to which like you view our theory as like right down to mechanism is questionable. It's like, what level do you pitch this theory? Yeah. Okay. Unclear. Okay. So that was just me talking, but here's some numerical optimization that backs this up. So again, I'm just optimizing these parameters and these frequencies, and here I've done it for 21 neurons over the representation of a 1D variable, and they fall into this one module, in this case, of with the same periodicity. You can look at the frequency spectrum, and it's got only 10 frequencies in it, 10 because there's 21 neurons, so less than half the number of neurons, 10 frequencies of decaying amplitude. You can do exactly the same arguments in 2D, so I'll go through these a bit quickly. You start off with some base frequency. Notice the choice of base frequency, which is currently arbitrary. Let's say this one. Add some waves, these pink wave vectors that peak at all the peaks and all the troughs. Produce a new frequency pattern that has new peaks, new minima, new local maxima. Add the new ones that push up all the troughs. Repeat, repeat, repeat. You get a grid cell with a frequency lattice, lattice and frequency space of decaying amplitude. And again, you can do this optimization. So in this case, it's on the torus, and you get this weird griddy shape. But so far, what I've said means that all different choices of grids to build this module with are equally good. Nothing in the argument I've talked about so far differentiates between different grid cells, as long as they're grid.
Yeah. Do you get square ones?
Yeah. Well, I mean, depends which optimization you do. And so you'll see in the next section when we get hexagons, why we get hexagons. And so if you remove the bits that get you hexagons, you don't get hexagons.
Okay.
Yeah.
So the things you just plotted there look a lot like when you take the argument vectors of the
Yeah. And so this argument is not what gets hexagons in our thing. And so if you do the same optimization without the later bits, you'll get squares. Cool. So that's why we get modules of grids. Now we're going to choose from amongst the modules of grids to get hexagons. And the bit that we're going to consider in order to do that is the chi and the p that I introduced before. So to recall what those are, chi was a term that said that there's a weighting of different pairs of points. And it's important to separate the points that are actually far away from each other. More important to separate those than neighbors. So the way we do this is chi is a function that depends only on the distance between x and x tilde and has some little length scale, little l. Beyond little l, you need to separate them. So chi is 1. Within little l, it's decreasing down to 0. So eventually it's 0, and you don't care about separating that pair of points. The second term was that on a 2D plane, animals only explore a limited area. So that's encoded in P, the occupancy distribution, which for the moment we'll take to be a Gaussian with a length scale capital L. So it's just like some length scale over which the animal is likely to explore. So these two terms will have two different effects on which frequencies you should choose to put in your code. The first term encourages low frequencies, because low frequencies are the ones that are roughly similar for points within length scale little l, but vary once you go beyond little l. So they're good at separating not neighbors, distant points. The other one pushes you the other way and encourages you to have high frequencies, because you want to make sure that within the length scale you're actually going to explore, capital L, your code actually oscillates, actually changes. So you need to have a higher frequency than 1 over big L. So these two effects together define like a target region in frequency space, this annulus between 1 over little l and 1 over capital L. And our game now is choose the grid, the module whose frequency grid packs the most frequencies into this annulus. And since the hexagonal lattice is like the densest packing lattice in 2D space, it's the best at doing this problem. You've got a square one on the right and a hexagon in the middle. It's the one that packs the most frequencies into the Goldilocks annulus.
So, for example, if you use, I don't know, but rather than a Gaussian, say a square distribution or something like that, then you'd end up with the square grids.
Not actually, because hexagon is the densest packing lattice in any shape in 2D space. A lot of them end up being. We'll discuss exactly this point towards the end, but it's more robust than just this choice of Gaussian.
Do you need the big L constraint in? I mean,
well, you get place cells if you don't do, because you'd want to squash, and what's the lowest frequency grid? Place cells.
Well, first, on the previous slide, your first constraint has both elements in there, right? Constraint 1 actually implicitly sets a lower and lower scale. We don't need constraint 2.
What upper scale does it set?
I mean, okay. Yeah, okay.
Yeah, I guess that's probably another thing. Kind of, I guess we've been arguing with reviewers about this. I think these are fundamental. So I think they're like any animal solving this problem in 2D space does need to think about the small length scale.
Did the reviewers think?
They thought it was a hack to get a frequency, bandpass frequency filter. But it's not.
That's how we review it, Well, if they're not, although there is an element of which viewers say it's true, these aren't hard customs.
No. Oh, sorry. Yeah, the illustration is just like an illustration. There's actually like smooth, right? The variation from 0 up to the first ring is like a smooth transition, and the outer one is just a transition.
And not necessarily symmetrically. Right? I guess it could be a lot worse. It's probably
symmetrical in 2D or symmetrical in like up and down function shape.
Symmetrical up and down. So having a bit over. Having a bit too much capacity is probably not as bad as not having enough capacity to disambiguate.
Yeah, shape of these could get quite common.
Not wanting to derail this, but like I know there's lots of recordings now of kind of place cells in really big environments, but now wondering kind of like to what extent is our understanding of RIS cells.
Yeah, that's a good point. Yeah,
like just because we've been recording in too small boxes.
Yeah,
and that's.
You're right. These could be. So there is evidence which we know. So grid scale isn't totally standard in large environments. So first of all, place scale really isn't like it's linked to various good reasons, probably linked to the amount of sensory information you can at a given point. So place filters on walls, if I'm small, around the middle of, if you're around in the middle of this room, there's nothing around you, place filters make right. So grid cells do something similar, maybe not quite pronounced, but this is for Mo's reanalysis of their own data. Which could be two things, right? It could just be an artifact of the fact you've got to stabilize the grid cells with place cells. Or it could be something interesting where like these two terms or something analogous to them are kind of a bit more dynamic.
Yeah. There are definitely a lot of like weird inhomogeneity effects you could put in that would probably shift the answers.
Yeah, exactly right. And indeed, the grids do also shift themselves. You could do stuff which would cause the scales to change and do things.
We'll be talking about some of those things, but maybe not quite the one you're mentioning later on. I think that's definitely an avenue for further work. But everything gets cut, the math gets a lot harder if you introduce like weirdness. And so here's the, if you optimize in a setting in which one module is optimal, so you'll see later that's controlled by sigma, with these two things added in, you get pretty clean hex. Okay, so that's hexagonal grids. The last step of this is why we would ever get multiple modules. So this works as follows.
I've got a quick.
Yeah.
So, and I'm guessing for you, your field size is actually related to the number of neurons you've got.
That is in fact one of the predictions we will talk about later on about the. We tried to look for correlation between the number of neurons and the ratio of the field size to the lattice size.
Yeah. Whereas it seems really. So you might have maybe not. We don't know fully the answer, but it seems there are a lot more small. At least people's ability to detect small scale grids seems to be way better than detecting large scale grids, which could be lots of reasons, but it could just be the more small scale grids.
Yeah.
But the ratio of field size to wavelength stays pretty constant.
Well, okay, I got some. Well, yeah, I don't know. I think it would make sense if it wasn't because like the sharper your field, the more you need to target. Like, so there's some intuition that backs up the idea that you would have more neurons in sharper fields. But we did try and check that, but we're trying to get torus and solid data to try and check it more quantitatively, as you'll see a bit. Okay, so the last bit we're going to talk about is the bit we haven't talked about very much yet, which is this first part of the loss. So what this does is we talked about already before. On the x-axis is the distance between a pair of points, and on the y-axis in blue is the amount that contributes to loss. You just need to push points further away than sigma from one another. Okay, and this changes the argument slightly, because let's imagine your code had frequency omega, that's this green one, in it. Then there are some pairs of points that are well distinguished from one another, but others that are not very well distinguished. For example, the two marked in pink. And then you've got a choice of which frequency to add in order to make the separation better. Well, actually, adding one that's twice the base frequency is a very bad choice because it encodes the same pair of points exactly identically. And so you're not getting any added separation for the pairs of points that are encoded the worst, separated the worst. Whereas adding something that oscillates at some other frequency, like 1.32 or 32 omega, does separate the pair of points that is otherwise not well separated.
Quite precise.
Yeah. And so you can like do a nice perturbative analysis of what the length scale sigma does, and it just penalizes pairs of frequencies, omega and omega prime, that are related by small integers. So if omega is 150% of omega prime, you get many more of these pairs of points that are like commensurately encoded, and therefore that pair of frequencies is penalized in your code. Okay, so we've now got a little bit of a harmonic tussle, which is that on the one hand, I argued that we wanted grids of frequencies, which are exactly those that are like simply harmonically related, like integer multiples of some base frequency, in order to get positivizability. On the other hand, we want to penalize those pairs of frequencies that are integer ratios of one another because they encode things really badly. Okay, and these two kind of like fight it out, and the resolution depends on the choice of sigma you make. That like sets the fight between these two forces. But a good solution in a large range of sigmas is for there to be multiple modules. In each module, the frequencies are harmonics of one another, so it's easy to positivize. But between modules, the frequency lattices are chosen to minimize the amount of like harmonic interaction, so it's best at encoding. And that's like what we claim would lead us to this kind of code.
And when you optimize your code, do you like also optimize? Sorry, when you like optimize the kind of the coefficients and stuff for your harmonic series, do you also optimize, say, the hyperparameters like the sigma and things like that, or so you fix them at the start?
Take some value and see what it produces.
Yeah.
So practically, what is the solution ratio that you've got here? Does that, I'm curious where you land in the ongoing debate of, is it, what do we have? 1.4, ratio of 2.
No definite answer. Yeah, I'm still trying to work out the number.
Which is probably the closest today's for
Not sure. It's quite hard to calculate. So what's something I'm also working on. So hopefully you got some intuition for why the optimization problem I presented led to the solution I also showed you earlier. The nice thing about like understanding things is you can use that to make predictions. You've now got an internal model of how this process works, and you can like play with it in your mind. So I'm going to use it to try and make some pretty predictions. And then I also introduced this problem without really talking about space for a while. So I'm going to like justify that a little bit by doing some non-2D space things. Okay, the first of these is one we've already talked about before. Here's your tuning curve. You add neurons. Adding neurons means adding more frequencies. Adding higher frequencies means you get sharper grid fields. So you can quantify that by looking at the ratio of mu, the grid size, to nu, the lattice length scale. And in 1D, you expect the number of neurons in the module to scale with this ratio, and in 2D, it's the ratio squared. So this is the thing I was talking about before. We went and tried and checked. I haven't got the data yet, so I just had to put those little blue bars on that roughly measure the size of the peak and the size of the lattice, and I put that ratio down there. So it doesn't quite just go, the smallest grid fields have the largest ratio. There's non-monotonicity in that the second one has, in fact, the sharpest fields. And on the right is the probability distribution. So how many of each grid spacing they found. So here are the 4 modules, these 4 green lines. And you can see that the one they found the least of is the one with the smallest ratio. And the one they found the most of is not the smallest one, but the one they found, the one with the sharpest grid peaks, this guy here. So I don't know that's all we got so far, but I'm probably going to test that on more data soon. Okay. Next up was this orientation question that was asked earlier. Hopefully this is what you meant. If not, ask again. So this is the following question. You've got a lattice in frequency space belonging to one of your modules, and you're choosing how to align a second lattice with it, with respect to it. So the way we're going to think about this is imagine standing at the origin, that point at which the 3 lines intersect, and staring out into space along some angle. And you'll see that these lines, the orange lines, are the densest ones, are the ones along which you'll see the most points. Okay, so those are the densest axes of the lattice. And as you rotate around, they'll get vary at their density. And so if you want to minimize the harmonic interactions between these 2 lattices, then overlaying the green on the pink lattices exactly with the same main axes is a bad choice because the densest axes are the two lattices overlap. So that's going to produce the most interactions. So you might like try and minimize that, maybe push it away to being furthest away from a line, i.e. at like 30 degrees with respect to one another. That's also a bad choice. So 30 degrees is the second densest axis of the lattice. So you're aligning the most dense with the second most dense. So you go through this kind of argument, and the way we're going to get to this is that eventually the best way to do it is slightly misalignment, maybe like something like 4 degrees. Okay, and so to quantify that, we just stand at this point, measure as a function of theta the density of points that you see, if you like smooth the points slightly, which is the amount of smoothing depends on the room size. And you get this plot, which is like the density of lattice points as a function of this theta. And then you overlay two of these lattices, two of these density plots, and like rotate them relative to one another by some other angle, delta theta, and you measure the amount of overlap. And you get this function that is like periodic, six-fold periodic, because there's like six-fold periodicities of both of the lattices, with like subsidiary maxima at this point 30 that are highlighted, and then minima in the function that are just at like 4 degrees from offset, either side of this peak. And the exact value depends on the size of the room and one other choice, the number of neurons in the module, but varies somewhere between like 3 and maybe 10. Okay, and then you can check that. So here's all of the modules, all of the animals in Spensola's paper that had multiple modules. And so along the x-axis is the orientation, and on the y is the spacing, and there's a density plot. So they use this to show that grids really neatly cluster into these modules, which are all the points that share the same lattice spacing and orientation. But I guess I'm using it to show that many of these modules are misaligned by some small angle, i.e. they're displaced from one another by a small amount along the x-axis. And when there are multiple modules, more than just two, which is actually quite rare, which you can also do the optimization for, it predicts they should be like a ratio of like one off by 3 and the next off by a little less than 3 and a little less than those kind of things. You get something like that popping out in the data as well sometimes. So that's that one. And the final one is about the shape of the room that we were talking about before a little bit. If you change the shape of this probability distribution the animal occupies. And so that's kind of easy to do. You just change P. So for example, this is the integral you would do if the room was a square room. And so what I'm going to draw for you now is the change in the loss if I place a frequency somewhere in the 2D plane. Okay, so it's like how good is this frequency according to this new change to the loss? And the yellow points are peaks in this function, and they're bad because positive is bad. And the the orange lines are 0, so they're good places to put frequencies. Okay, and so you still see the main effect is there's a high frequency bias due to the room size. So you don't want to be anywhere near the origin. That's all bad. That's all yellow. But beyond that, in addition to that's the same structure we had in the Gaussian case, we've additionally got like these orange lines that you want to line. So there's this choice of like good frequencies in this room that turn out to being frequencies at which you oscillate a lattice, an integer number of times within the length scale of the room, along either the x or the y axis. And you can do the same thing for a circular room, for example, and you get the zeros being instead like zeros of some Bessel function. So different results. But I guess the first thing is that you could like make some predictions about which grid length scales you should get in different rooms. And you can get some things, for example, imagine overlaying a hexagonal frequency lattice on these two plots. In the circular case, you can see how a hexagon would fit nicely on the circle. The inner ring lies on the orange circle, and then the other ones lie outside. In the square case, it's quite hard to align one of these hexagonal lattices on top of the inner orange square. So you'd expect some skewing away from perfect hexagonal like lattice-like behavior in a square but not circular room. And one slightly more precise one is that you can do things like what would happen if you change the room, because that changes what's optimal. So people have done this experiment. They measured grid cells in a square room and then squashed one of the room length scales to 2/3 its original length. So if you think about what this is doing along just this y dimension, it's changing the optimal frequencies from the integer ones shown on the bottom, which are these 3 purple frequencies, to the new integer ones, which are the green ones above, which are like more widely spaced because the length scale is smaller. Okay, because it's like inverted. And so you can look, and they have make some predictions. Maybe which one will, if you had a grid cell at purple frequency, where would it go? Green frequency, and hard to say for some of them, but certainly the one which is optimal for both of them should probably stay in that frequency. Okay, and so they do this. They measure like there's a grid cell, pair of them, measured in both these environments that looks like roughly a 1 length scale grid cell that squashes to another 1 length scale grid cell. Here's a roughly 2 length scale grid cell that squashes to another roughly 2 length scale grid cell. And here's one that was a 3 here, roughly 3 length scales, but squashes to being a 2 length scale grid cell. So it's exactly this case where this purple guy jumps and stays at the green point there.
It's really the experiment we want to do to test that, though, isn't it? Like,
I mean, what would be great is if someone measured the grid cells and then phoned us up and was like, which ones are going to stay the same and which one's going to go different? And then you measure.
that would be better. I mean, the problem with this and the way we did it originally was the animal, I think, because that's the stem solas doing that experiment, right?
Yeah.
I think they did it the same way we did it. It's the same, it's a familiar environment. They then lift the animal out of, squash it up and put it back. So you've got sort of this horrible confound between the fact that presumably the grid is now stabilised relative to centrifuge walls. So it's not a, it might be testing what you think, or it might be just testing the ability of centrifuge to reset the existing grid or not. Which can predict this, right? So imagine you've got nice tight boundary cell tuned to the bottom wall, for instance. If you knew it's got to line up with the grid, that it's like, first environment, plasticity, attached to the peak. Now, as long as you move the wall so it always lies on a grid peak, everyone's happy. There's no like. So you get the same picture. What you want is
new environment.
Total new environment.
Yeah, that'd be great.
Someone must. In fact, wait. Did we do that? We sort of did that. When we did one of the control, we did this experiment in 2007, and we did it both directions. We just squashed the grid. I don't know if it's going to have enough information for you, but we also, half the animals we put in the rectangle first and stretched it. So you do actually get to see the grids recorded in an asymmetric environment, which should make sense.
I should check that.
Can I ask why in those experiments, so in the original, this is kind of like mimics the Keith and Burgess stretchy box, right? But why did you choose a different, like they did it where they halved the dimension or doubled the dimension?
Why did I do that? It's because, indeed, we probably got lucky, but I think if you change it quite too much, the animal just decides it's somewhere else. We did it by that much because we didn't know what would happen, right? At the time, everyone was saying, oh, grid cells, this like, people were going around saying it's just pure path integration, they're not related to anything, which was clearly never going to be the case. And on the other hand, you've got these existing placeholders, they get highly influenced by geometric change to the environment. And so I needed something that I would be able to measure the result whichever way it goes. I need to be able to see enough grids. And if I made it half as small, I might only be able to see like one line of fields, I wouldn't be able to measure anything. So it was also a lucky guess.
Can I ask, maybe I missed something here. So if you were to reproduce this with your optimization, with the grids that fall out of that, you'd have to rerun with different constraints, right?
You have to make, so in order to make this prediction from our numerics, you have to make the assumption there's some stickiness in the grids that they want to be at frequencies they were previously at. So you could try, for example, initializing the optimization rather than from random like we normally do, but initialize it from the position at the end of the first optimization. I haven't tried that, but something like that.
But how would that fit sort of with the behavior result that you observed that in one trial in a box for the animal, the change?
I mean, I don't think we were ever claiming that our optimization was what was going on in the animal, implementation-wise. I don't know. I guess we're assuming that there's some other is optimizing the code beyond gradient descent on some loss that we made up.
So you'd say, if I were to extract sort of a high-level summary from you, you would say this is sort of the mathematical justification for what happens by other means in the real neural network?
Making a normative theory of where it should end up, not how it gets there.
Okay, thanks.
All right. Okay, very nearly done. The last thing I'm going to think about is beyond 2D. I described this framework, and it can work for any as-is. It can work for any variable whose transformations form a group. You've got to find the appropriate representation theory of that group, and then chunk through the same steps that we did here. So you can do it on a circle, and you get head direction cells popping up. We can go on spheres and get things like modules of place cells, or grid cells on spheres, or these weird pole and orbit cells on spheres and things like that, which are all related to like spherical harmonics. People have like spent a long time looking at them. One that we wanted to apply it to is like 3D. People have measured 3D grid cells. So when you optimize, you do get like very pretty looking 3D dense packing lattice type tuning curves. But that's not what people measure. They measure these, which look a bit weird. We did a similar optimization where we chop out the actionability and only require functional and biological parts. Okay, so a positive code that separates points pretty well, but doesn't have this property that the matrices exist. And in 2D, they look like that. So they're like multiple bumps in the tuning curves, but not ordered in a lattice-like way. Which kind of makes sense. The lattice is bad for encoding because it means that there's like rules about how the points are arranged relative to one another that mean that points are optimally encoded differently. So you randomize the position of those bumps and you get a better code. This is kind of the intuition. And you can do the same thing in 3D and get like weird bump patterns that you can't really see inside. But yeah.
What would that mean? That would mean all the things we think grid cells are good for suddenly get away. Right? You can't, I think it's great.
In this 3D space, yeah. That's exactly. So it's, I guess it's maybe you're in 3D sacrificing navigation for efficient encoding, but only in 3D, perhaps not 2D, because it's more pixels. I guess would be something like the argument.
For what it's worth, I'm only really familiar with the Roddy Green's experiment on this, which was going on whilst I was doing my PhD, and it seemed to like a lot of the actual behaviour. I can't do it on bats, but the behaviour seems. He kind of seemed to think it was to do with the fact that so this lattice, you're not really like. So I'm thinking about your occupancy distribution, right? And I'm also thinking about that in terms of like maybe not even occupancy, but like a transition distribution. For example, like there's a lot of effort to go up, like to go up there, like lattice and stuff, whereas to go down lattice or even along the thing. Effort. He seemed to think that was some sort of like perhaps one of the things that might have been that was hard, like it was near impossible to control for this.
Yeah, I definitely think, and there's also these. This is now his data, I believe, and they've like projected the autocorrelation on the X and Y planes, and it does seem like even. So he reports these ones that are like column cells that look like grid cells but extended in Z. But there's also these ones that like have strange amounts of like structure in their autocorrelation, even on including the Z direction a little bit. So I don't think the end of the story is like there's zero structure in 3D grid cells. I mean, I guess I'd be surprised if that were true. And so I've been trying to adapt the framework slightly to be like, because you rarely have to integrate a very long way in the Z direction, right? A rat might climb like a few meters, but it goes like, I don't know, kilometers, in the other direction. And so you could try and change the framework such that X and Y were much more important from an actionability point of view. Maybe do something rather than our precise one that says you have to be actionable. So you have to be actionable up some error threshold, and that error threshold is set by the length scale you travel in the different directions. And that might lead to like different predictions that maybe look like that. I've been chatting to Gilly Guinness, who does that ones, about whether there's like structure in those ones, which she seems unsure about. Structure like in a looser meaning structure.
I mean, rats. Is it fair to say rats didn't like evolve to naturally navigate very well in 3D, or is that not true? Because because they're not talking about the optimization here, so maybe there's just no way for rats to optimize their grids to do good actionability in 3D.
It's one of the square lattice.
The brown rats we use aren't so much climbers, whereas the smaller black rats, they are climbers.
I mean, what's the natural setting for a rat, like back
in the bushes?
15,000 years in the bushes. Yeah. So like the sewers where you're like climbing.
Yeah. Okay. Maybe I'll just wrap up quickly. I'd like to test these predictions. I'd like to relate actionability to the mechanistic models. And there are some things our theory will never predict. And so there's some other ideas about how to get those in there that we kind of talked about as well. And then you can draw all sorts of structures like hierarchies of structures, multiple variables, things like that. 3D thing direction. But hopefully you're convinced. We've studied a representation of an internal model using 3 normative ideas. This different encoding of different inputs using some like principles, plausibility principles, and this idea that you can predict the consequences of their actions. From that, we've got like multiple modules of grid cells and their perturbations normatively. Got some testable predictions. And I guess the broader idea is that this is like a normative framework in which to go beyond just encoding and biologically plausibility. We want to put models in, and there's a lot of places that might apply. So I guess next I'm trying to work on prefrontal cortex stuff for these ideas. That's that. Thank you.
That's great. And thanks for explaining it so clearly. There was one thing that I was kind of thinking about, and I don't. The reason why I'm saying is that I don't even know how to factor this into the way that you're framing it. But it's kind of like you have your occupancy distribution and stuff like that. But there's also it's also kind of like a positional uncertainty distribution, which is almost like the inverse of that, assuming you're in some sort of open field with some you're not really capturing that aspect of it. So I was wondering how much that level of uncertainty would affect the grids. But
I guess the way that I've been seeing that is the length scale sigma. For example, here can be thought of as like a noisiness measure.
Yeah, but it's consistent throughout.
It's the same everywhere. You could vary it. You could also, it's like Gaussian, which is a terrible assumption for neural firing, like noise. Plus one would be the actual one.
You could actually, I mean, you're doing this iteratively, right? So you could vary your sigma could vary with the position in space as well.
It would have to be the pair of points, I guess. But
I mean,
But
that would be a way of factoring it. I'd just be interested to see, because I mean,
that might be a good way to get these.
There's evidence that the grids, the grid field, because you're also talking about the grid field sizes and stuff, right? But there's some evidence that the grid field sizes are bigger in the middle of the environment and stuff like that. So
and the novelty shrink is possibly rather not to relation expansion. More likely uncertainty expansion, so that would fit with which we have a model of.
So in that you would end up kind of like assuming it's like this where the sigma is kind of fixed, but it's like over learning your sigma would be getting smaller, you're getting better at discriminating between 2 points.
It could be two things, right? It could be your lower bound is just higher because you don't know where you're not aware of the cues or whatever is available. The inherent uncertainty is higher. Or it could be even the upper bound shifts to, for a given environment, the upper bound shifts to some sort of vanilla baked-in value, and then it's tuned to whatever's broken, and baked-in value is higher. Presumably they're also not symmetric. So in a 3D example, little l is probably bigger in the z-axis, but big L is probably small. Actually, someone should go. Presumably, Minkowski's have some measures of that range in the X and Y is massive. And they presumably have something about transition probability. I bet they fly at one level and then drop down and do another thing.
There's also a question in the chat, but do you want to go first?
Okay, just quickly.
You did with him. You can ask him anything.
I'll make it quick. So it feels like we apply lots of these biologically plausible constraints onto the representations. And then we just say, we act on it with a certain weight matrix. So we don't, maybe that's biologically plausible, but we're not applying such stringent constraints onto how we actually use this code as to what this code itself looks like. Have you thought about this?
So I think if you don't constrain the way in which your actions operate on the circuit, actionability is not a constraint, right? If you're then you just define your function to be the one that maps all points to the point one step north everywhere in space, and that doesn't mean anything. So we only got a constraint because we force this action to happen through a matrix. Okay. So I guess the reason I'm saying that is it justifies your concern because how you implement this action is vital to the whole scheme.
So for example, have you thought about constraining this matrix to be satisfying Dale's law or something?
It
has to all be positive or negative. I don't know.
The one I've spent a long time playing with is this matrix exists in a continuous attraction network. There's an infinitesimal generator of the translation, which is like the infinitesimal little matrix you apply. Unfortunately, it's not a matrix. It is a matrix that scales with the size of the step, but it's got a few nonlinearities going on inside it that mean it's not quite what I've studied here. But it's very hard to. The only reason we do that step of what does actionability imply is because mathematicians have spent 100 years doing that for matrices, and they haven't done it for continuous attraction networks. And so hopefully the discrepancy isn't too large. I guess but there is a discrepancy.
Okay, so the question in chat, and I'm really bad at reading out loud. It's going to get called up because it's a very longer one. Harsha says, in the beginning, you referred to the other normative theories for grid emergence, and I guess many of the predictions would also fall out of those models, question mark. So is there a way to disambiguate them or identify the common or related assumptions that explains either the periodicity of the multiple packing modules or hexagonal packing? For example, does successful path integration implicitly need actionability? Sorry if I missed it.
So what was the last bit? The successful path integration?
Does successful path integration implicitly need actionability?
Yeah, so the second part's easier because it's basically the same as the last answer in a weird twisted way, because it depends what you mean by path integration. But if you're doing path integration by applying matrices and then asking for the point that you end up at to be distinguishable, that's just our functional actionability constraint. So in our depends what you mean by how you path integrate, but under a particular interpretation, yes, exactly our framework is path integrating. But you could imagine different ways of doing path integrating that might apply different constraints. And so it's not like universally path integrating.
So I think the question is like how could you say, or how could you test this versus say some distortion stuff or the Ryland?
Yes. Yeah. Let's see. So I think a lot of the ideas of the older efficient coding stuff. So let me try and get just without my smarmy joke. Yeah. So a lot of the older stuff that's just like efficient coding things could derive some of the same like normative reasons for doing like grid morphing or angles between things as R1 gets. Because basically, once you get to grids and decide they're hexagons, you're kind of at the same point. You can follow the same arguments, I suspect. So I haven't worked through. These are slightly different frameworks. I'm not sure that's true, but that would be my guess. The other ones, I guess a lot of these approaches struggle to get multiple modules. Sorsha gets them, but only because of a discretization of his like position grid, I believe. So you get which predicts things like root 2 and root 5, but only because that's like the nearest neighbors on a square grid, things like that. So I suspect that isn't correct for that reason in that to that level of accuracy. Other ones to distinguish it from. And we're very similar to the last two I mentioned down at the bottom here, which is Gow and Whittington, because we use basically the same theory, but extend it to multiple modules and explain why it works, I guess is the goal. So other things to distinguish it from. I don't know if that's a good answer.
Seems.
Yeah.
Yeah. I had one last question actually, which is to do with, so I know this isn't really meant to be kind of like a learning grid cell sort of model, it's more kind of like establishment. But maybe there's other parts of the model that do have predictions. For example, like those weights that you're using to move to kind of like transition through, say, a tractor network or something like that. Like, how would you hypothesize that gets implemented? You'd have to have like these sort of like shifter cells almost, but in
as I say, there's for example, if you choose the nonlinearity of your continuous attraction network to be a square f of x equals x squared, then the continuous attraction network is updating itself through a matrix, and then you can directly compare our matrices to matrices in there. So that's the only case I think where it's true. Other ones are like more approximate. The other thing that puts a spanner in the works there is that we assume we don't have time in our thing. We just like, which isn't so much of a problem, but makes comparing anything but like the infinitesimal step a bit meaningless. So, I don't think that's like a terrible thing, because you get around the can by doing like a lot of infinitesimal steps in the same way that you apply a lot of infinitesimal matrices in our thing to get around the thing. But it makes comparing, that's the one that you would compare, and maybe that would make sense. I haven't looked hard into that, but maybe I should. Yeah.
Cool. Great. Thanks again. Yeah.